Welcome to lecture 6 in this video lecture series on the topic operating system. In this lecture, we will be talking about process scheduling. So far in the course, we have seen the concept of process, how to create process, how to work with process. And in this lecture, we will be talking about how an operating system helps in managing different processes running on a CPU. We already seen the concept of multitasking, that is, when a number of processes they would like to execute on a CPU, and how the OS helps in sharing the CPU time among the processes. So today let's talk about the different scheduling algorithms, that is the different algorithms by which you can choose which of the processes would actually be allowed to run on the CPU. Okay. So before we go into the discussion of the algorithms, let's quickly recap the life cycle of a process. We already have seen that a process goes through a number of states during its execution. When it starts, that is when the process is created, we call that it is in the new state. Once the process gets all the resources it needs, that is all the OS allocates the sufficient memory space to that particular process, and the process is loaded onto the memory, we say that the process is in the ready state. And once the process gets loaded onto the memory, the CPU is instructed to execute the process, and the CPU starts executing. And in that case, we say that the process is in the run state. And finally, when the CPU completes the execution, so the execution is over, then we say that the process has terminated. So it starts, gets allocated to the memory, the CPU executes that, and finally it terminates. So that's how a process, the life cycle of a process moves. Okay, but during the execution of a process, there are certain instructions which the process is not privileged to execute. I mean, the instructions in the process are not allowed to be executed being in the user space, and they are only to be executed by the kernel. That means the kernel executes them on the behalf of the process. And how does the kernel know that these instructions have to be executed? So the process, when during execution, it puts a request. Let's say a request of an IO. But since the request cannot be accessed by, the IO access cannot be done by the process, so obviously it's the kernel that has to do. But during the time when the kernel is executing those instructions on behalf of the process keeps quiet. So it needs to be in the wait state, right? So that is why whenever there is an IO request, the process is taken out of the CPU and it waits for the IO access to be completed. So when the IO access is over, then the process once again becomes ready so that it can be executed. So it again moves to the ready state. Okay. So if you look at the total cycle of the life cycle of a process, you find that overall it is these three states in which a process moves. It's either executing, that is being run by the CPU, or it is in the wait state, or it has completed its wait state and it is again becoming ready so that it can be taken up by the CPU. So if it is only one single process, then you have either an execute state of a process or you have a wait state of a process. So that's the situation if you have only one process that is currently running in your system. So either the process is executing or it is waiting. So this is the loop in which a process moves during its life cycle. So if you look at, or if you represent this in the form of a timing diagram, so that is, you represent the process execution, say a process called P, during its entire life cycle, it is either executing, we represent that with this shaded figure, or it is waiting. So we'll put a gap to represent that this is the wait period. So this is the wait, and this is the execute period. Okay. So once the wait is over, it again executes for a certain amount of time. It again hits a wait, that is some IO request, and it again waits for some amount of time, then again it is available, so it can execute. So you see the entire, and maybe here the process ends. So if you look at the entire timeline, you find that there are small time units during which the process was executed, and there are time units when the process was in wait state. Okay. So these time units in which the process was executing, we call that as a burst, an execute burst, or we call it a CPU burst because it was executed on the CPU. And the time duration during which the process was waiting, we call that as a wait burst or an IO burst, because the wait was due to IO. So overall, the entire life cycle of a process consists of a number of wait bursts and a number of CPU bursts. Okay. And what is the total time duration of this process? You may say this is the total time duration of a process. If I say that the instant of time at which the process completes its execution, if we call that as the completion time, okay. So if I say that this is the completion time CT, and this is the time at which the process became ready to be executed, so we call that as an arrival time, that the process arrived here. Okay. Arrived at what? Okay, we arrived at a certain queue. We'll talk about that later. So for the time being, let us assume that this is the time when the process became ready, and this is the time when the process completed, that it's terminated. And the difference of these two timing instants, that is CT minus AT, is what we call the turnaround time. And this is the time that the process was actually executed, the total amount of time it took to complete the process. And if you see this turnaround time, it consists of a number of IO bursts and a number of CPU bursts. So this turnaround time was some CPU bursts and some IO bursts. So that led to this entire turnaround time. Okay. But this is the story if you have a single process that is working. Okay. But we know that in order to have a high performing system, we would like to utilize these spaces, because during this wait bursts, okay, so during this IO burst, the process is not on the CPU, right? The CPU is not executing that. And there is some IO that is being accessed. So what is the state of the CPU there? The CPU is keeping quiet. That is, it is wasting some cycles. And the basic idea of a CPU is to run a process. So the aim is to keep the CPU busy as much as possible. The CPU should not wait. It should do some work. And the work that it's supposed to do is execute some process. So if this is what happens in a single process, that is, sometime the process is not executed and the CPU is waiting for some process, why not allow some process to be executed when one of the process is in the wait state? So suppose this is process number P1 and the process P1 is waiting for some IO during this period. Now instead of keeping the CPU waiting, the better option would be to allow another process, another ready process, to start execution during this wait cycle. Okay, this is what it is. Maybe that when it finishes some part of that, then you may again allow P1 to resume. But this kind of sharing of this time of CPU between these two processes would eventually keep the CPU busy and will have a higher performing system. So this is what the idea of multiprocessing is, that when you have multiple processes that are available in your system and one of the process goes into a wait state, instead of waiting for that process to come out of the wait state, you better take that process out of execution and allow a different process to run on that. That is what the idea of multiprocessing is. Okay. But now the question comes, if there are more than one process that would be allowed to execute within this wait cycle of P1, what would be the condition then? What would happen? Means there is not only P2 but then P2, P3, P4, P5, all of them are there. There are more than one ready process which is available and which can be allowed to execute within this time. So now there's a decision to be made that which of the processes should now be allowed to be executed. Okay? And that is all about scheduling. That is making a decision that which of the processes should be allowed to execute when one process goes into the ready state. Okay? And who does that? So obviously, this decision has to be taken by the operating system, right? So the OS, the OS decides the allocation of processes to the CPU. Right? This is the job of the operating system. Okay, now in order to do this job, there are two modules in the OS, or I say the kernel, okay, let's put it like this, that performs this decision making. So this decision making process that we are talking about is what is called process scheduling. That is deciding which process to run next when one of the process goes into a wait state. Okay. What are the two modules that perform this? So the first module that does this decision making is called the scheduler. Okay. So this is the module that actually makes this decision, that it finds out which of the processes P2, P3, P4, P5, which one of them is the candidate to be executed next on the CPU. Right? And how do you do that? Okay, we'll talk about different algorithms, 3 to 4 of different algorithms based on which the scheduler will be able to decide. So the scheduler will be designed according to a particular algorithm. Okay. Now this scheduler that is going to perform which will be performing this decision, where does it find these processes? And how does it perform that? Okay. So interestingly, what the scheduler maintains is it maintains a queue of processes. So this is the so what it does is it maintains a queue of processes, and this queue is called the ready queue. Okay. So it's actually maintains a queue of, you can say, ready processes. So all those processes which are currently ready, so a queue of them is maintained. So whenever a scheduler has to take a decision that which one of the processes would be allowed, what it does is it looks up to this ready queue and picks up one of them from this ready queue and allocates it to the CPU. That's what the scheduler does. But you may ask, when does the scheduler perform all this? When does it look up to this? Because the process is going on, right? A process is currently running. Let's say some process called P1 is running on this system. When does this scheduler being triggered? When does this scheduler finds out that now it's time to take a decision to find out the next process? Okay, so there are 4 situations when the scheduler performs this decision making. The first is when an IO request is made by the currently running process. Okay. So when you have a currently running process that makes an IO request such as this, which automatically means that the process which was running has made a request for some IO, and that will be accessed, or the request will be granted to, and the request has been made to the kernel, and the kernel is supposed to perform that IO access, and which automatically means that the process moves into the wait state. So because the running process has moved into the wait state and the CPU has become idle, so there is a decision to be taken that is there any process in this ready queue? If there is at least a process in this ready queue, it should be allowed to run. It should move from ready state to the run state. So the scheduling has to be done here. and the scheduler will pick one of them. So this is the situation when a currently running process moves into the wait state because of an IO request, and if there are processes in the ready queue, a scheduler will take a decision to pick one of them and put it to the running state. Okay. Now, when this IO request is over, okay, which means that you have some process which was running, it went into wait state, and then the IO request is over. Okay. When the IO request is over, now it also becomes a candidate to be executed, but it is not put directly to the run state. Rather, it should go and sit into the ready queue. Though its IO request is over and it was originally running on the CPU, doesn't mean that it immediately gets a chance to be executed. It has to go and sit into the ready queue, and then the scheduler will, according to its decision-making policy, would decide whether that process which was earlier running should be given a chance or some other process will be given a chance. So it's not necessary that the moment your IO request is over, you will be immediately given a chance. You have to go into the ready queue. So it's just an indication that, okay, I am also now one of the ready processes. So my IO request is over, please consider me as well according to your policy. So this is also the situation where the scheduler can make a decision. Okay. Then we have the third, where we have, there's a situation where even if the process has not terminated, we know that a process moves from new to ready, then ready to run, and then terminate. But there is a situation when the process may not terminate, yet you take that process out of the run state and put it in the ready state. What I mean is, there can be a transition from this state to this. Okay. But why? We'll see there are algorithms where we decide that, okay, even if the process has not completed its execution, we associate a certain timer with that, okay, or a time slice, you may say. And if the time slice of that particular process during execution expires, even if the process has not terminated, it will be taken out of the run state and put it in the ready state. I repeat. So this is the situation where a process will be taken out of the run state and put in the ready state when the timing instant or time slice associated with that particular process expires before its termination. The process had still some time to go before it would terminate, but the time slice associated with that has expired, and as a result the process is taken from the run state to the ready state. So this is one kind of an scheduling policy where we associate some time slice with every process, and during the scheduling we find whether the time slice has expired or not. If the time slice has expired, then even if the process has not completed its execution, that it has not terminated, it is taken and put in the ready queue, and some other process is given a chance. So this is the third condition where you have on account of a timer interrupt. Timer interrupt means your time slice has expired. We'll see one of the algorithms where this is made use of. And then we have the usual process, that is a process terminates. So if there was some process which was running and the process terminated, so obviously there are other processes which are in the ready queue and one of them should now be given a chance. So these are the situations where at which a scheduler, so these are the situations for scheduling. So a scheduler comes in the picture when one of these situations occur. Right? And the job of the scheduler is looks up to this ready queue, finds one of them and allocates it to the process when any one of these four events occur. So this is one of the modules that actually performs this decision. Okay. The next is, there is one more module which is there in the kernel related to this scheduling decision making, and that is called a dispatcher. Now this is the module that actually allocates that particular process to the CPU, the one that has been decided by the scheduler when one of those conditions occur. The decision has been taken by the scheduler, and now it's the job of this module called dispatcher to dispatch that is to provide that particular or allocate that particular process to the CPU. So that is what it does. And this process of switching from one process, taking one process out from execution and allowing another process to be allocated to the CPU is called context switch. So dispatcher, the job of the dispatcher is to perform something called context switch, right? So it's like you have this CPU, the CPU was executing a certain process P1, and then P1, some part of that was executing, and here you stop this. After executing this, you stop process P1 and then allow P2 to start execution. So moving these processes from the execution mode to the ready mode and swapping them from the CPU is what we call context switch. But this context switch has an overhead associated with this. An overhead is because you see, when a certain process was executing on the CPU had updated a lot of things in it. A lot of registers, a lot of memory was written or read during the execution of P1. Now suddenly you switch from executing P1 to executing P2. And according to the scheduling policy, you may come back to executing P1. So that means when you leave the execution of P1, the state of P1 needs to be saved so that when you come back into executing this process P1, you should start from that same point, right? So that means the state of the P1 should be saved when you make a context switch. So what does this saving mean? Saving means saving the contents which are necessary so that you can start from the same point when you come back to executing P1. And this saving of the contents or saving of the state of P1 involves a lot of data writing onto the memory. So that is the amount of time that is spent in performing those operations. So what you have is the context switch actually has an overhead, and this is in terms of time. So you spend a lot of time in performing those state savings, overhead due to state saving when you move from one process to the other. So this is the latency that is there whenever a process is taken out and another process is allowed in. Okay, and because this allocation process, etc., this is being taken care of by the scheduler, and scheduler is part of the kernel. So these two modules, they themselves are programs which are run. So when a scheduler is running, it's being run by the kernel, so there are kernel level instructions. When the dispatcher is running, it's again a kernel level instructions that are being executed. So obviously, when a process P1 was executing and suddenly it stopped and a context switch has to be there, then the control goes to the kernel because these two modules have to be run and this. So when the kernel is executing the scheduler and dispatcher, obviously the CPU had changed its mode to the privileged mode, right? So on a context switch, the first thing that happens is the process is stopped, the currently running process is stopped. The current process is stopped, that's the first thing to do. Okay. 2 is you save the states, save the state. 3 is you switch mode, okay, because now you have to execute these two. So the CPU switches the mode to the more privileged mode. Then these two run. The scheduler takes a decision that which of the process in the ready queue should be executed. Then it allows the dispatcher to send that particular process to the CPU. And then it has to again, so then we have the scheduler that runs. Okay. Scheduler and dispatcher, they run. because it's the kernel level code. Then we have, once the allocation has been done to the CPU, you again switch mode, because now you should allow P2 to run, and P2 is a user level process. So in this case, the switch mode was from user to kernel level, and now this case from the kernel level mode to the user level mode. And finally, you instruct the CPU to start executing the next instruction. That means you load the CPU, the program counter of the CPU with the instruction, the corresponding address of the instruction from where you would like the instruction of execution of P2 to start. So this is overall how the scheduler and the dispatcher, they work together. Now let's talk about the different algorithms which the scheduler utilizes in order to decide which process would be allowed to execute on the CPU next. And we are going to talk about the scheduling algorithms. But before we talk about these algorithms, there are a few parameters that need to be discussed, because all the algorithms that we are going to talk about, they have their own pros and cons. So when should a particular process, an algorithm be utilized, under what circumstances, under what kind of situation? So it's important to compare them, and this comparison will be done based on certain parameters. The first parameter that we'll be talking about, so let me first talk about some parameters, and we call them the scheduling criteria. So the first parameter that we are going to talk about is CPU utilization. And this is the one that we have already been discussing about when we said about multiprocessing. That is, we want the processor to be busy as much as possible. Okay. So CPU utilization means the idea is to keep the CPU busy. Now the main job of a CPU is to run a process. You don't want a CPU to remain idle. So your scheduling algorithm should always focus on allowing the CPU to be busy. So you would like to have a maximum CPU utilization. The next that we are going to talk about is something called the turnaround time. You already have seen that. Okay. What is the turnaround time? It's the total time of execution of a particular process. And we said that it's mathematically, it can be written as the completion time minus arrival time. The time at which the process completed minus the time at which it arrived, that is, it became ready. So the entire, the difference between these two instances of time is what we call the turnaround. This is the time that a process spends in execution. Okay. And this is the amount of time to execute a certain process. And we want this time to be as minimum as possible. Okay? Because you don't want processes to take longer time of execution. You want them to be executed as fast as possible. So it is expected that the turnaround time is minimum. The third is a parameter called throughput. Now this refers to a set of processes. So when there are a number of processes in your ready queue, that is, a number of processes have become ready and they can be executed, you want your CPU to execute these processes as many as possible per unit time. So you want to complete as many processes within a certain time period. So this is the measure which says the number of processes which have been executed per unit time. So if you are able to find some time duration, find out how many processes got completed. So you would like to have a maximum throughput. So you would like to complete as many processes executions as possible. And then we talk about the fourth parameter, and this is called waiting time. Now what do we mean by waiting time? We already have seen that processes in their life cycle have either they get executed on the CPU or they wait. Now this wait involves waiting of this I/O as well as the time that a particular process spends on the ready queue. So we are not interested in, so when I say wait time, I'm actually not interested in the time that the I/O access has been, the time that the I/O access took, because that's the kernel that is taking care of. When I say wait, I mean that the process was waiting for the I/O to be over, and once the I/O was over, it did not get into the CPU, the execute mode or the run mode immediately. It had to wait in the ready queue. So what I'll talk about is the amount of time that the process spends in the ready queue. Okay. So when I say wait time, I actually mean the amount of time a process spends in the ready queue. Now there can be a lot of such waiting bursts during its entire life cycle. So if you sum them up in its entire lifespan of a process, the total of those waiting bursts is your total waiting time. So this is the time at which the process spent in the ready queue. We will see that this is an important factor which determines how good is your scheduling algorithm. Now we also have one more which we call the response time. And as the name implies, now this is, oh by the way, if we have discussed about waiting time, what do you expect the waiting time of that particular, what should be the aim of the scheduling algorithm? To have a minimum waiting time. Because if you want a particular process to be executing, you want it to be executed by the CPU. You don't want a process to keep quiet and remain in the ready queue. So the focus of this, of any scheduling algorithm should be to run a process. You don't want the process to keep in the ready queue. So that is why the waiting time should be minimum for any process or for a set of processes. So for a single process, it is the individual waiting time, which should be less. And if you're talking about a collection of processes or a set of processes, the average waiting time of all those processes should be minimum. This is the aim of any scheduling algorithm. The minimum the waiting time for a set of processes, the better is the algorithm. The second, the last parameter that we are going to talk about is, it's called response time. And this is the amount of time a process takes, the amount of time it takes from a process submitted until its first response. When I say first response, I mean the process came and it may not be that it got a chance immediately to be executed on the CPU, right? So it was created and it came and it waited in the ready queue. Now, the time at which it arrived and the time at which it was first given a chance to get executed, the first execute burst of that particular, the time duration between them, between these two instances, is what we call the response time. Okay. So time at which it arrived and the time at which its first burst got its chance to be executed. So that is what we call the response time. And the idea or the aim of any scheduling algorithm should be to have a minimum response time. Okay. So with this 5 scheduling criteria: maximum CPU utilization, minimum turnaround time, maximum throughput, minimum waiting time, and minimum response time, we'll see how different algorithms, different scheduling algorithms, how they perform. So let's begin with the first one. And the first algorithm that we are going to talk about is called the first come first serve. Or we call it the FCFS scheduling. So as you may have guessed from the name, it's the most simplest of all the algorithms, and the idea is that the processes which came earlier will be allowed to execute first. So it's absolutely dependent on the arrival time. Whoever came earlier, you put them in that particular order in the ready queue. So obviously the one which is at the head of the queue is the process that came earlier. So gradually as the processes they come, they are pushed into the queue, and the one which is at the head of the queue is the one that came the earliest. So it's a simple algorithm which says that a process that came earlier will be served first. Okay. So, or a process with minimum arrival time is served, is allocated next. So if you have to make a decision, you look at the arrival time of all the processes, find the minimum of that, and that is the process that should be allocated. Let's understand this with a simple example. So we have a set of processes. Let's say we have 3 processes, okay, and we also have their arrival time. I will call arrival time as AT, and I will have the CPU burst time, we will call them as BT, and along with that, we will be computing something called the completion time. Okay, so let me write it as to save some space. CT is completion time. Now we also have TAT. We already have discussed about this. This is the turnaround time. Okay, so this is turnaround time, and then we have WT, which is waiting time. Now, there's a relation between turnaround time and where CT and BT. We already have seen that TAT is CT minus AT, that is completion time minus arrival time. That's the total time spent by the process. And if you see that this TAT, it actually, so within this entire time duration of the process, a process spent some time in execution, that is, it was executing, there was some CPU burst, and there was some IO burst, which was the waiting time. So W2 in that sense is TAT minus BT. So this is the relation we'll have. So if I have AT, BT with me, I will be first scheduling the process, I will be getting the completion time of each one of the process, and then I will be using CT and AT to compute this, and then I will be using this and this to compute this. So this is the whole idea. Let us take an example where you have some processes which is given to me, and say the processes that are given is P1, P2 and P3, and I have their arrival times, all are 0. That means all arrive at the same time, and their processing, the burst time is 2433. Okay. Now, let us try to schedule these 3 processes according to first come first serve. And in order to do that, we will be using some timing diagram to represent that. And the timing diagram that we will be using is called a Gantt chart. So we will be using this chart to explain the scheduling policy. Okay. So what is the total time range that we'll have? It will be sum total of all these three, 24, 3, 27 plus 3, 30. So it will definitely be ending at 30. And it will be starting at time instant t equal to 0. So this is the time that we'll have. So this is, let's write it here, this is time. And on top of that, I will be representing the status of my ready queue. Okay. So this is also time. So let me show you the contents of the ready queue vis-a-vis the scheduling. So let's begin. Because all have arrived at time t equal to 0, so all the processes are there. But out of that, let us assume, because all the processes have arrived and the arrival rate is the one that decides, all are equally probable. Let us assume that, okay, P1 will be scheduled first, then P2 and then P3. Let's decide on this schedule order. Okay. Because there is no order to decide based on arrival time, let's assume that this is the time. Let's see what happens. So if we assume P1 is scheduled next, so automatically P1 gets its to schedule first. P1 executes. If P1 executes, the other two must be in the ready queue. So P2 and P3 is in the ready queue. They are in the ready queue. Okay. And let's write P3 first and then P2, so that we understand that okay, P2 is in the head of the queue. And P1, it takes 24 units of time and finishes off at time instant 24. It finishes off at time instant 24. And at 24, because a process has completed its execution, remember the scheduling events. So the scheduler comes in the play because one of the process has terminated. What does the scheduler do? The scheduler looks up to this ready queue and finds out one of the process that should be allocated next. Because the process P1 has terminated, so the CPU now will go into an idle state, but it should not. So one of the process will be picked up from here and be allocated to the CPU. So the process that will be picked up is the head of the queue, because this is the process that assumed to be the one we allow to execute next. So P2 will be allowed to execute next. P2 takes 3 units of time, so it takes 3 more units of time and it finishes its execution at 27. So when P2 had started executing, what was the status of the queue? There was only one process P3 that was there in the ready queue. And P2 finished off its execution at time instant 27. So at 27, again one of the process got terminated, so it's time for the scheduler to come in. The scheduler comes in and looks up to the queue and finds that okay, there's only one process called P3. It allocates P3 to the CPU, and P3 continues for the next 3 units of time and finishes off at 30. Okay. So you see at 30 units of time, all the 3 processes, they complete their execution. Good. So let us write this down. What is the completion time of P1? P1 completes at 24. What is the completion time of P2? P2 completes at 27 and P3 completes at 30. So once we have filled up the CT column, let's compute T80. T80 is CT minus 80. That means this minus this. Okay, so it's these two. 24 minus 0, which is 24. Then we have 27 minus 0, which is 27. And we have 30 minus 0, which is 30. So this is what we have. Okay. Now what is WT? WT is TAT minus BT. So it's between these two. Okay. That means 24 minus 24, which is 0. Now we have 27 minus 23, which is 24. And then we have 30 minus 3, which is 27. Okay, so this is WT. Now, once we have this, why don't we calculate the average WT? Let's see what the average comes up. Average is 0 plus 24 plus 27 by 3, and that comes out to be 17, something like. Okay, so we have yeah, it's like 17. So this is what we have as our waiting time. What about response time? The average response time. What is response time? Let's recall. It's the time that a particular process arrives, the time duration between the process arrival and the time of its first response. When did the P1 first got its response? Right at that time, T equal to 0. So basically there is no response time, there is no time duration for the P1 response, because P1 arrived at time T0 and immediately got a chance to be executed. So it did not wait, that is the reason why the waiting time was 0. It did not have to wait, and it got its immediate response. So the response time in case of P1 is 0. What is the response time of P2? Response time P2 is P2 arrived at 0 and got its chance at 24. So the response time of P2 is 24 minus 0. Okay. So if you can calculate the average response time, response time average, so we will see that one is 0, the other one is 24 minus 0, the third one is, what about P3? P3 came at 0 and got its first chance to execute at 27. So it's like 27 minus 0, and this entire thing by 3, which is nothing but the same as this waiting time, and it is also 17. It may seem to you that okay, waiting time and response time are same, but they are not. We'll see that later on, that there will be differences. But however, this is how we compute the first come first serve algorithm. Okay. Now let us do a thing. Let's try to change this a bit. Okay, let's try to change the order a bit and see what happens. So remember, in this case, when this was the scheduling order, we found the waiting time to be equal to 17. Okay, so in this case, the average waiting time, the average value, that came out to be 17. Now let's try to change the order a bit. Okay, so what we'll do is we will take a different order and we'll try to schedule this again, and we'll be computing this completion time and TAT and average values of WT once again. Let's see if we have any changes. So let's take the schedule order to be maybe P2 first. Okay, so let's take P2, then we'll have P3, and then we'll have P1. So let's do it in this way. So if this is what happens, let's say this is our Gantt chart that we're going to draw, and this is the status of the ready queue. So, okay, so now the order is P2 first, then P3, and then P1. So that means P2 came and immediately all of them came at the same time, and P2 immediately got a chance to execute. So this is the Gantt chart we are showing. Obviously P2 is executing, so the other two processes, they also have come, but they will be sitting in the ready queue. So P1 and P3, they will be sitting in the ready queue. But P2 just takes 3 units of time. So P2 completes its execution at 3. So this is T equal to 0. P2 completes its execution at 3. Because P2 completes its execution, obviously the scheduler comes in the play, and scheduler now picks up one process from the queue. It's say P3, and it allows, so here we have P3 gets executed. Because P3 gets executed, the only process left in the queue is P1. So P3 again takes 3 more units of time, it finishes off at 6. And once P3 finishes, again the scheduler looks up in the ready queue and finds that there is only one process left. So that process is now allocated to the CPU, which is P1, and P1 completes its execution at time instant 30. So this is pretty similar to, it also completes at 30. But now let's see what is the completion time of each one of them. What about P1? P1 came at 0, but it completed its operation or execution at 30. So the completion time of this is 30. Completion time of P2 is 3 and completion time of P3 is 6. Now let's try to compute TAT. Remember what is TAT? TAT is completion time minus arrival time. So these two, 30 minus 0, which is 30, 3 minus 0, which is 3, 6 minus 0, which is 6. This is TAT. Now what is waiting time? Waiting time is turnaround time minus burst time. So 30 minus 24, that is 6, 3 minus 3, which is 0, 6 minus 3, which is 0. That's what you have, WT. Let's calculate the average waiting time. And average waiting time in this case is 6 plus 0 plus 3 by 3, which comes out to be 3. Oh my god. So in this case, your waiting time average is 3. Look at the difference. Okay. The same set of processes, the same arrival time and burst time values, but merely changing the order of the processes in which they execute has a huge difference in the waiting time, the average waiting time. Previous case it was 17, in this case it's 3. This is a very interesting thing to be noted in case of first come first served schedule. So what is the thing that we observe in this case is that in FCFS, the scheduling order of process has an effect on the average waiting time. Okay. And what is the thing that we observe is this particular scheduling algorithm, it depends on the order of processes. Okay. If you select a particular order of processes to schedule, you have a certain waiting time. If you change the order, you have a different waiting time. And interestingly, you see, look at this first order. In this case, you had a process P1 was scheduled which had a longer burst time. So a process with a longer burst time was scheduled first, then the processes which had smaller burst time, and in that case the average waiting time was 70. But when we changed the order and we allowed the smaller burst processes to execute first, we found the burst time to be 3. Which clearly says that if you allow longer burst duration processes to execute first, it eventually causes your system to slow down. That is, the waiting time is more. Okay, and this effect of allowing longer burst duration processes to execute than the smaller burst duration processes, this particular effect that we have is called the convoy effect. Why is it called so? The name has been obtained from the convoy of fleet of vehicles that move on the road. Okay. So if you have, let's say, a number of cars that are moving at a certain speed, maybe 100 kilometers per hour, if suddenly there's a truck that comes in front of them and the truck is moving at 60 kilometers per hour and you do not have enough space for the cars to overtake the truck, then what will happen is, as long as the truck remains in front of that particular fleet of cars, the cars, though were moving at 100 km per hour, now have to follow the truck and move at the rate of 60 kilometers per hour. Why? Because if there is one single vehicle, which is a slow moving vehicle, that eventually brings down the speed of all the vehicles which are behind that, even if they happen to move faster than the vehicle which is in front. So this is a convoy that we say, right? The convoy of vehicles. And the entire overall speed of that entire convoy is dictated by the slowest moving vehicle, if that slowest moving vehicle is at the front of the convoy. That's exactly what it says. So this is 3 processes And if the process with the slowest or the longest execution time, it happens to come first, then that slows down all the processes, even if they were faster, that is, they were having lesser execution time, but the overall system execution time came down. This is the problem that is present in first come, first serve schedule. Okay. However, there's an advantage to this algorithm as well. The advantage is that it's a very simple algorithm to implement. You just saw that it's nothing but a simple implementation of a queue. So all that is required is a queue is necessary to implement this FCFS. But this convoy effect present in the FCFS algorithm, that is a major drawback for this kind of scheduling technique.